So here in this problem we have a block hanging on a cord, and the cord is being used to vertically lower that block, which was initially stationary. It has a mass m and it's moving downwards with a constant acceleration of g over 4. Remember here g stands for the gravitational acceleration due to Earth, and it's 9.8 meters per second squared. When the block has fallen in distance d, the question will be to find the work done by the cord's force on the block, the work done by the gravitational force, and the kinetic energy of the block at the bottom of that movement. Let's look at the forces first. We have the gravitational force downwards, and we know the magnitude of it is mg. We have the tension of the cord, which here I'll call it tension. I'll mark it as T. It points upwards. I also have an acceleration, so I'll mark it here next to my free body diagram to remind me that the acceleration is constant with a magnitude of g over 4, and it points downwards. Looking at Newton's second law, we will have to add all the forces. In this case, we have only two, and they all they're aligned along the vertical direction. So I'm going to choose the positive direction to be up. So that means that the vector for t will have a positive vertical component. The vector for the gravity will have a negative vertical component. So my equation will be t minus mg has to be equal to ma. Remember, the acceleration vector also points downwards, so its vertical component has to be taken as negative. That's why I have written here minus ma. Or I can also write as minus mg over 4, since I know the value of the acceleration. That gives me for the tension to be equal to mg minus a quarter of mg. In other words, the tension or the force in the cord is 3/4 of mg. Here m was the mass of the block and g was the gravitational acceleration, 9.8 meters per second squared. With that, I'm ready to look at part A and see what the work of the force of the tension or the force in the cord is. We're going to start with the standard formula here for a force that has a constant magnitude, and it keeps its direction relative to the displacement constant as well. So we're going to have magnitude of the force times the distance times the cosine of the angle between the two. I know the force and the displacement is also given by the problem. The direction of it is downwards. The block moves from a higher location to a lower place, and that displacement is d. The angle between the force and the displacement is 180. However, because the tension is the force in the cord pointing upwards, it's holding the block upwards, and the displacement is downwards. So let's write this. For the tension here, for the force, the magnitude of it will be 3/4 mg. For the displacement, it will be d. And for the cosine of the angle, I will have cosine of 180. Remember, cosine of 180 is minus 1. So the work done by the force of the cord on the block will be minus 3/4 of mgd. The minus means that tension is actually removing energy from the block's kinetic energy, which is a good news in this case. If tension was not removing the corresponding amount of energy, the block will be falling with much higher acceleration and will be eventually acquiring much more kinetic energy. Now let's look at the work of the gravitational force. The work of the gravitational force again will be the magnitude of the force, the magnitude of the displacement times the cosine of the angle between the two. In this case, the magnitude of the force will be mg, that's the gravitational force. The magnitude of the displacement is once again d, and here the angle between the force and the displacement is 0. They both point downwards, so cosine of 0 is 1, and so I can see that the work of the gravitational force is equal to plus mgd. Now let's look at the kinetic energy. We will use the work energy relation in terms of the kinetic energy. So here I have written as the change in the kinetic energy is equal to the work of all forces. Remember, when we use this work energy relation in terms of the kinetic energy, we have to count all the forces. which is okay because we already know what the work of all the forces is. So the change in the kinetic energy is going to be equal to the difference between the kinetic energy at the bottom location minus the kinetic energy at the top location, which is 0 because the block was initially stationary. Remember, that is what the problem tells us. So that has to be equal to the effect of all the two forces, minus 3/4 mgd, that's the effect of tension, plus mgd, that's the effect of gravity. So we see that the kinetic energy at the bottom location will be 1/4 of the mass of the block, the gravitational acceleration, times the displacement. I couldn't resist here to show you how I would solve this problem if this was not a textbook problem or it did not show up on the test and someone did not force me to actually calculate the work done by the gravitational force. If this is a real life scenario and someone comes in and says, okay, what will be the kinetic energy of the block? I will actually use the total mechanical energy and work with the potential energy. In fact, virtually all my friends and physicists that I have known will actually go and work with the potential energy and the mechanical energy. We will not be calculating the work of the gravitational force. But as things stand, this is a good practice for you to learn how to calculate the work of gravity. But let's see what happens in a realistic situation. Someone would ask you what will be the kinetic energy of the block, and then I would personally set up my ground here as y0 at the lowest location. That means the top will be y will be equal to d. And then I will use the work-energy relation in terms of the total mechanical energy, which is the change in the total mechanical energy is due to the work of only the non-conservative forces. In other words, I don't want to calculate the work of the gravitational force, which is a conservative force. I just want to work with the potential energy. So usually, always, it's either or. You either work with the potential energy or you have to calculate the work of that conservative force. Since my preference is for the potential energy, here it is. The total mechanical energy at the very bottom will be the kinetic plus potential. But remember, the potential at the bottom will be the mass times gravity times the location, the vertical location, which I chose to be 0. So that means I will have no potential energy at the bottom. I'll have only kinetic. Then I have to subtract from that the expression for the total mechanical energy at the top. At the top, the block, of course, is stationary, so it means my kinetic energy was 0, but I had potential, which was equal to mgd. And that has to be equal to the work of only the non-conservative forces, which in this case is the work of the tension or the force in the core, which is minus 3/4 mgd. So see here that as far as the kinetic energy goes, we end up with the same result. We have to take mgd and subtract from it 3/4 of mgd, and we end up with the same result, that the kinetic energy at the bottom will be 1/4 the mass of the block, the gravitational acceleration, times the displacement.